Hello, everyone. Thank you so much for joining this webinar today. My name is Allie Yamagata from Saint-Gobain, North America, and I'm the YPN Cements Division Liaison. I'll be your host for today's webinar. Before we start, I'm going to give you a quick introduction about ACerS and the benefits of being a member. Can you all see my screen? Check. Okay, you guys can see. So and like today agenda. Okay. So I'm gonna talk a little bit of before we start that being a member of ACerS gives you access to resources that allow you to continue to learn and grow, gain recognition with awards and scholarship, apply for support to travel, and attend conferences. I'm going to quickly talk about the ACerS membership path, depending on where you are in your career. If you're a student, we have the Mature Advantage Student Program. If you're a graduate researcher, you have the Global Graduate Research Network. We also have an associate membership. If you are a professional and have never been involved in ACerS, you can join us actually for free for 1 year. And then the second year is only like $40. So, and that will actually give you discounts if you attend our conference. So yeah, you actually like save some money by joining ACerS. And the individual membership after that would be $120. One of my favorite things about ACerS is the mentorship program. We actually are open for sign up for the 2026 program by December 12th, 2025. Make sure you join this. This is really nice. We actually have a mentor program for faculty, students, and industry. So if you're early career professor in the university, you can actually have a mentorship for someone who's more senior in the professor, for example, or like you be in industry and you're just starting your first steps in industry, you can actually be matched with another person from industry that can help you. And also we have the student mentorship program. This is a very nice program. I highly encourage you to also sign up for this. And so this webinar today is brought to you by the Cements Division. And so who is the Cements Division? So we're one of the 11 divisions of the American Ceramic Society. We advance the fundamental materials science of cement with an emphasis of nano to micro scale research and develop new technologies for you. There's a lot of opportunities to connect, meeting and event, resources, leadership, development opportunities, and awards. We organize the annual meeting, the Advancing Cement Material Based Materials meeting. We're gonna release soon the dates for next year, and this is a great conference, so I highly encourage you to participate. We have also sponsorship opportunity for this conference. They're already open. If you're interested to promote your brand, it's a science-based meeting focused on the world's most used concrete material. There's a lot of opportunities now, and if you're interested, you can contact Vicki Evans at the email there, or Professor Pernoy Ceremony. You can contact both of them, and then you can provide you more details. So today I would like to introduce you to today's speakers. Is Professor Hee-Jeong Kim. Is an assistant professor of the Department of Civil and Architectural Engineering and Mechanics at the University of Arizona. Her research focusing on developing sustainable and high-performance construction materials through the valorization of industrial waste to create resilient and low-carbon infrastructure. With expertise in AI-driven modeling, multi-scale materials characterization, and 3D concrete printing, she designs innovative construction materials for both Earth and future space applications. We will have a Q&A session after the talk, but feel free to submit your questions during the presentation. We'll only respond like after it, but yeah, please submit. There is a Q&A box there, and you can like send your questions as we go over. So I would like to give the floor to Professor Hee-Jeong Kim now. Yeah.
Thank you so much for the introduction. Let me share the screen. Okay. So, hello everyone. It's a great pleasure to be here today as part of the ACerS webinar series. My name is Hee-Jeong Kim, and I'm an assistant professor in the Department of Civil and Architectural Engineering Mechanics at the University of Arizona, with joint affiliation in Material Science and Engineering and the School of Mining Engineering and Mineral Resources. So today I'd like to share my research on how we can better utilize resources both on Earth and beyond. This talk will focus on two key areas. First, the valorization of mining waste as a sustainable construction materials here on Earth. And second, the concept of in situ resource utilization or ISRU for building infrastructure on the moon and Mars. Both topics share a common goal, transforming what we already have into what we need, whether that's reusing industrial byproducts or leveraging extraterrestrial materials for future human habitats. So this presentation is about resource utilization, and I will be discussing three connected research topics. First, I will start with our study on understanding early hydration dynamics and the CSH formation with using Raman spectroscopy. This work helps us see how cement reacts and gains strength during early hydration, providing the fundamental knowledge needed to develop more sustainable materials. Next, building on this understanding, we will explore how industrial waste materials, such as mine tailings, can be used by studying their chemical composition, activation mechanisms, and reactivity in cementitious systems. Then, once we understand how tailings behave, we'll look at how machine learning can help us move from waste to resource using data-driven modeling to predict and optimize the performance of tailing-based construction materials. Finally, we will take the idea of resource utilization beyond Earth and explore in situ resource utilization, how we can build with what's already available on the moon or Mars. So as we know, early cement hydration is important because it controls how cement sets, gain strength, and develop its microstructure, forming the foundation of all cement performance. However, the factors and mechanisms that drive these early chemical and mechanical changes are still not fully understood. So, a deeper understanding of this stage is essential for improving cement performance and for designing sustainable materials, including those made with mine tailings or even extraterrestrial resources. So many researchers are trying to understand the early stage of cement hydration with using different experimental techniques such as SEM, TEM, and CT scans are used to observe how the material change over time. These techniques help us see the formation of hydration products and understand how cement hardens in the early cement hydration stages. To track the chemical changes that happen during early stage cement hydration, researchers also use techniques such as XRD, TGDTA, and FTIR. These methods help us identify the chemical reactions, monitor phase changes, and understand how hydration products develop over time. However, most of these analysis methods are invasive and the samples can be damaged during preparation steps such as crushing, heating, or vacuuming. However, Raman spectroscopy is a non-invasive method that can overcome these disadvantages. It allows us to analyze chemical and structural changes in cement without damaging the sample, making it a powerful tool for studying early stage hydration. Therefore, Raman spectroscopy is ideal for tracking the early stages of cement phase transformation And in this study, I used Raman spectroscopy to observe the cement hydration process, both spatially and temporally. This method allows us to identify the hydration products as they form and evolve. The goal of the study is to understand the dynamics of the early stage cement hydration process and to gain insight into the structure and formation of CSH, which is the main strength giving phase in cement. So Raman spectroscopy is really useful because each chemical phase has its own unique spectrum, like fingerprint. So by using Raman, like we can actually identify different hydration products easily, even in a heterogeneous material like cement paste, just like what you can see in this figure. So this figure shows that the basis spectrum of the like all cement hydration phases, hydrated phases. And by using this technique, we can map the Raman images and track the hydration process of calcium silicate in situ over a 24-hour period. You can see the time lapse of these process on the video on the right over here. Um, and the Raman spectra used for this mapping, including those like calcium hydroxide and silicate phases, are shown in the figure on the left. So from the Raman mapping result, we can clearly see the alide, which is C3S, is gradually consumed by during hydration, while calcium hydroxide continuously increase over time, confirming the progress of the hydration reaction. In contrast, belite, which is a C2S, shows no significant changes during this period because it mainly contributes to the later strength development of concrete. So one of the main advantages of Raman spectroscopy is its ability to identify different hydrated phases in cement, such as a CSH, gypsum, ettringite, monosulfate, and water. And the OH symmetric stretching peaks appear in the range of 3,000 to 3,700 per centimeter, and they can be categorized in four different types: free water, bound water, COH, and the SiOH. So in this study, we focused on the OH symmetric stretching peaks, particularly the CaOH containing phases, to better understand the hydration reaction and the formation of a CSH during the early stages of cement hydration. So OH bond can be found in many different components on cementitious materials. Here are the OH profiles of calcium hydroxide and the disordered calcium hydroxide. And lastly, CSH, which is calcium silicate hydrate, are compared. So both CH and CSH contains OH bonds, but their Raman peak position and peak width are different, reflecting their unique chemical environments. So by decomposing the peak profiles, we can identify the local environments of the OH bonds and gain insights into the structural difference between these hydrated phases. So this slide shows an animated plot of the CaOH peak position and width. By tracking these values over time, we can clearly see how the CaOH peak changes during the early hydration process. From this analysis, we discovered a new phase, which is an amorphous or disordered form of a calcium hydroxide, which we call like disordered calcium hydroxide DCH. We found that this disordered CH acts as a precursor to crystalline calcium hydroxide forming before the setting process begins. This discovery give us new insight into the early hydration mechanism and helps explain the formation pathway of calcium hydroxide in cement. So from the CSH spectrum, there are three types of OH bond can be identified: bound water, CaOH, and the SiOH. Based on this observation, we can infer that CSH exhibit a broad bound water peak and an OH peak slightly wider than that of CAH with a right-hand shoulder, suggesting structure complexity. And there are numerous structure models for CSH have been proposed, and our Raman spectrum strongly supports Gartner's model over here, which describes the CSH as a disordered layered structure containing both CaOH and the SiOH bond. Raman spectroscopy can be used not only to study OH phases, but also to differentiate the various surface phases in cement. The Raman mapping image shows that a large amount of ettringite is already formed within just an hour of hydration over here. And it helps densifying the cement matrix structure, contributing the early strength development and stability of the material. And this Raman technique can be applied to various types of cement research as demonstrated in following researches. So first study is activation and the reactivity of mine tailings in cementitious cement systems. So as you know, the big problem with the concrete is the carbon emissions from the cement production. Since concrete is the most used material in the world, this has a huge environmental impact. Cement production releases a lot of CO2 because it needs high temperatures and chemical reactions that produce carbon dioxide. As a result, it is responsible for about 7 to 8% of global CO2 emissions. To solve this problem, researchers are trying to develop alternative cements and reduce the carbon footprint of concrete. And one good way to do this, to use supplementary cementitious materials or SCMS as much as possible. These materials can partly replace Portland cement and help lower emissions while still keeping good performance. So in the mining industry, one of the biggest challenge is the accumulation of tailings. And every year, billions and tons of tailings are generated and stored, yet most of them have no practical use. These tailings can cause serious environmental and health problems, such as acid leaching and contamination of soil and water systems. And they can also become a part of the ecosystem, creating a long-term risk for surrounding communities. In addition, managing and storing these waste is very expensive, requiring large area of land and continuous monitoring. So if we look at the chemistry of mine tailings, most of them contains a lot of silicon, iron, and aluminum oxides, and some also have calcium oxide. And this composition is very important for making cement. And according to ASTM 618, pozzolanic material should have at least 70% of silicon, iron, and aluminum oxide combined. And most mine tailings already meet these requirements. This means that tailings have good potential to be used as a supplementary cementitious materials or SCMS. And based on their potential, mine tailings can be used in many different ways in construction materials. Tailings with a high amount of silicon oxide can be used as a precursor for geopolymers, and they can also serve as a like supplementary cementitious materials to practically like use as a like replacing the cement materials. And some tailings can be added to the clinker kiln during cement production. And depending on their particle size, they can be used as a fine aggregate or coarse aggregate in construction. So tailing offer many possibilities to replace natural resources and reduce environmental impact in the construction industry. In general, crystalline materials have like particles arranged in a regular and stable pattern. Because of this structure, they are usually less reactive, and the most minerals in mine tailings are crystalline, which means that they do not easily react in cementitious systems. However, to make tailings reactive in cementitious systems, they need to be amorphous, where the atoms are not arranged in a regular pattern. Amorphous materials are less stable and it can react well in an alkaline environment. So, if we want tailings to participate in the cement hydration reaction, we need to convert their crystalline phases into amorphous one to make them more reactive. Therefore, our first research focuses on the activation and the characterization of mine tailings to improve their reactivity. The main idea is simple. We need to add more energy to the material to break the crystal bonds, make it amorphous, or help it rearrange into a more reactive phase. And there are three main activation methods. The first one is mechanical activation, which breaks particles, increase surface area, and creates structure defects that like make the material more reactive. And the second one is thermal activation, uses a heat to change stable crystalline phases into amorphous ones. Under the right condition, it can also form new and very highly reactive phases. And the last one is chemical activation, which uses alkaline or acidic solutions to dissolve minerals and create the new reactive binding gels. In our research, we mainly focused on using mechanical and thermal activation methods to study how tailings can become more reactive in cementitious system. So in this study, we used gold mine tailings or GMT. The analysis of a GMT shows that it contains several crystalline phases, including quartz and calcite, which are important for cementitious binders. It also includes clay minerals such as orthoclase and muscovite, which are mainly silica and aluminosilicate-based materials. In addition to these, GMT also contains a pyrite and sulfate-bearing phases. These are problematic because pyrite can oxidize and produce acid mine drainage, which is harmful to the environment. And if it is not treated properly, it can also cause sulfate attack when we use in like cement-based materials. And after the characterization, about like 18.7% of the material is amorphous, and which is a reactive portion that can contribute the cement hydration. So we were able to confirm like amorphous phases are like 18.7% in our gold mine tailing samples. And for activation, we used like mechanical and thermal methods to increase the energy and break the crystalline bonds, making the tailings more reactive. For the material, mechanical activation, the raw tailings were ground for 60 minutes in a disc mill running at the 500 RPM. And for the thermal activation, after grinding, the samples were heated at 800,000 and 1200 Celsius degree. And after heating, they were rapidly cooled or quenched to prevent the crystal forming again. So all activated samples were analyzed using XRD and Raman spectroscopy, and we performed the like quantitative phases analysis with a about refinement, and if each refinement showed a goodness of fit below 1.5, which means the result is very reliable. And since our goal is to use these tailings in cementitious materials, we tested their reactivity using compressive strength test, TGDTA with checking bound water analysis, and Raman spectroscopy. And finally, Raman mapping was used to identify the reaction product and confirm how reactive material became. So after the activation, we first looked at the XRD results to see how the phase changed. After the mechanical activation, there was no significant or no big change. As you can see, the material stayed mostly in crystalline. However, at 800 Celsius degree, with applying the thermal activation, we saw major changes. Pyrite and chloride broke down completely and producing new phases like hematite and anhydrite formed. And this shows the start of a higher reactivity. And at 1000 Celsius degree, autoclase changed into sanidine, meaning the structure was rearranged by heat. And at 1200 Celsius degree, most crystalline peak disappeared, meaning the material became most amorphous and more reactive. And we were also able to compare their chemical phases with Raman spectroscopy. And as I mentioned before, Raman spectroscopy helps us identify each minerals by its unique vibrational fingerprint. It allows us to see where different phases are located in the sample through Raman mapping. And in this study, we used Raman spectroscopy to confirm the formation of new phases and to check which original phases remained after the activation. And the phase distribution map clearly shows the presence and the spatial distribution of these new and existing phases, such as anhydrite and hematite and sanidine. So it is important to know how much of each phase is present before and after the activation, because this can be related to their activity. And to measure this, we use the Ritubel refinement for phase quantification. And 800 Celsius degree, we saw major changes. Pyrite and chloride completely decomposed and forming hematite and anhydrite. And at the same time, calcite dropped from 8.46% to 2.29% due to decarbonization. And the amorphous content also increased to about 29%, making the beginning of a higher reactivity. And as the temperature increased further, the amorphous content rose from 19% in a raw material to almost 95% at 1200 Celsius degree. And this shows the higher temperature break down crystalline phases and create highly reactive amorphous material. And the easiest way to evaluate reactivity is by looking at the compressive strength with the checking strength index. And according to ASTM C618 standards, a material is considered pozzolan if at 20% of replacement of OPC, it reaches at least 75% of the strength of ordinary Portland cement. So it means like if it reaches 75%, that means the SAI, which is a strength activity index, is 100%. So from this graph, we can see that the raw GMT and mechanical activated GMT show low strength compared to OPC. And this is expected because they still contain main crystalline and unreactive phases. But when GMT is like optimally like treated with like 800 Celsius degree, the strength increases significantly and becomes comparable to PC sample. And this improvement happens mainly because of two factors. First of all, like the formation of anhydride, which supports the hydration process, and the increase in amorphous content, which makes the material more reactive. And at higher temperature, like such as 1,000 Celsius degree and 1,200 Celsius degree, the strength starts to decrease again. This drop is related to the loss of anhydride and changes in phase composition. So overall, the thermally activated GMT at 800 Celsius shows the best performance, achieving more than 100% SAI. And now that we have achieved a higher strength, we wanted to know whether the tailings actually reacted or just acted as a filler. And one way to check this is by measuring the chemically bound water, which shows the degree of hydration. And the chemically bound water becomes part of the crystal or gel network of the hydration product, like CSH or cash and CSH. And when the sample is heated, the OH group in these structures are released, causing weight loss. And that weight loss tells us how much water was chemically bound. And we follow the method B of ASTMC 1897 standards. And the result shows that the 800 Celsius degree activated sample has the highest amount of the bound water, which matches well with the compressive strength results. And this confirms that the thermal activation at 800 Celsius not only improved the strength, but also enhanced the reactivity and the hydration of the tailings. To further confirm the reactivity of the activated tailings, we performed the reactivity test and the TGDTA. And these tests help us to see how much CH was consumed during the hydration. And this shows whether the tailings actually participated in reaction. And the result shows that the 800 Celsius activated tailings, which had the highest compressive strength, also consumed more calcium hydroxide. And this means that they are more reactive, and this result is clearly supported by TGDTA data. And the TGDTA curves also suggest the formation of a hydration product such as tringite, monosulfate, and CSH, which confirm the real cementitious reaction happened. And to find out which hydration product among tringite, monosulfate, or CSH formed in a larger amounts, we used the Raman spectroscopy on the R3 reactivity sample activated at 800 Celsius degree, which shows the best performance. And after just an hour, the Raman spectra, which is shown in figure, revealed the formation of the AFM phase, especially like CA4, Al2OH, 12X, and H2O. And these spectra were used to track and analyze how the hydration product evolved over time, helping us understand the reaction mechanism of the activated tailings. And in the modified R3 test, calcium hydroxide was mixed with the supplementary cementitious materials and cured at 50 Celsius degree for 10 days. And the Raman spectra collected over time were used to observe these changes. On the slide, you can see the raw basis spectrum and the distribution taken after an hour, and the raw distribution map shows that the AFM phase keeps growing over time, and this confirms that the main hydration product formed during the reaction is AFM phases. So the key findings show that optimal thermal activation plays a crucial role in improving the reactivity of mine tailings, and that this happens by increasing the amorphous content and forming reactive anhydrous phases. And at the optimum activation temperature, anhydrate and other reactive phases are formed, while pyrite and other unwanted minerals are completely decomposed. And these changes lead to better performance of the material in cementitious systems. And we also found that up to 30% of cement can be replaced with activated tailings without losing their strength. In fact, the strength improves, and this approach supports the sustainable use of mining waste in construction materials. So the second study focuses on the machine learning guided reuse of copper mine tailings with machine learning is important because it allows us to make data-driven decisions to optimize activation conditions and mix design. And this helps us deal with one of the biggest challenges in using mine tailings, their compositional variability, and by applying machine learning, we can predict material performance, reduce trial and error experiments, and save both time and resources in developing sustainable construction materials. Since we both know the construction and mining industry face serious environmental problems, we applied machine learning to efficiency optimize the mix design and target strength, thereby accelerating the development of a sustainable construction materials. And the economic sustainability of using mine tailing is supported by many case studies that shows significant cost saving and new revenue opportunities. In this study, we carried out two separate experiments using copper mine tailings to develop sustainable mixed designs. In first, we used the copper mine tailings as a partial cement replacement in cement paste, and in this case, cement was replaced from 0% up to 20%. And second, we used the copper tailings as a partial aggregate replacement in mortar, and here sand was replaced from 0% up to 10%. And these two approaches help us understand how tailings affect the performance of different construction materials and how we can optimize their use both for the sustainability and strength development. And to train our machine learning model, we needed a data set that included both mixed design information and compressive strength results. Because data on materials containing copper mine tailings is still limited, we used the public database of concrete materials, even though it is not including tailings. That database contains 1,030 data points. And for the study one, where copper mine tailings were used as a partial cement replacement, we created our own 31 data points with the experiment. And for study two, where tailings replaced sand, we generated the 15 data points with the experiment. And we focused more on study one because we wanted to test how machine learning predicts compressive strength with different CMT, like copper mining tailings contents, and water to cement, water to binder ratios, and curing times. And study 2 included fewer variations. And after combining our experimental data with the public data, the total data set included 1,061 data points for study 1 and 1,045 data points for study 2. And this table shows the input and output parameter we used in study 1 and study 2. And as I mentioned earlier, the open source database include the data on the concrete materials containing cement, slag, fly ash, water, plasticizer, coarse aggregate, and sand. And in this data set, the mix design and the curing age are used as input parameters, and the compressive strength is the output. And for study 1, our samples were cement paste, so the input parameter were cement, water, copper mine tailings, and curing age. And for study 2, the samples were mortars, so we put the input parameter included cement, water, sand, copper mine tailings, and curing age. Both studies, the compressive strength was used as the output parameter for the machine learning model. And since we combine the open source data with our experimental data, the input parameter now include the cement, slag, fly ash, water, plasticizer, coarse aggregate, sand, copper mine tailings, and curing age. And when a variable was not available in either data set, we simply assigned it a value of 0. For example, in study 1, we set zeros in the CMT column for the open source data. In contrast to for our experimental data, we assigned zeros to the BFS, fly ash, superplasticizer, coals, and fine aggregate columns. And in machine learning, we always need training data to build a model and testing data to check its performance. And a common rule is to use 80% of data for training and 20% for testing. And in study 1, this rule was applied only during hyperparameter optimization. And the hyperparameters are adjustable settings that help us improve the model's accuracy, and optimization help find the best combination of these values. And in study 2, we applied the 80 to 20 split for the entire prediction process, from training to testing. And to check whether our small experimental data set could be combined with the open source data to build like reliable machine learning models, we look at the correlation coefficients between variables, and the combined data set provides a different and more representative data distribution, which is important for the modeling materials containing copper mine tailings. And for study 1, we used 3 machine learning models, and among them, the random forest model went through hyperparameter optimization, where we tested 5 key parameters and found the best values with using Bayesian optimization. And for study 2, we used 10 different machine learning models based on literature to explore which one performed best for this type of the data. And in this case, we did not optimize the parameters. We used each model with its default setting to compare their baseline performance. And all modeling and analysis were done with using Python's machine learning package, scikit-learn. To evaluate how well each machine learning model performed, we used several performance metrics, and the numbers are shown on the slide indicating which study used each metric. And for example, like score was used in both study 1 and study 2 to measure how accurately the model predicts the compressive strength. And these metrics help us compare model performance and determine which algorithm works best for predicting the behavior of materials with copper mine tailings. And the test result for mixtures with different amount of coppermine tailings shows that the compressive strength decreases as both the water to binder ratio and the CMT percentage increases. And a sharp increase in strength is observed during the early curing period from 1 day to 7 days. And after that, from 7 to 28 days, the rate of the strength gain becomes slower. But however, the cement paste with the CMT never reaches a higher compressive strength than the control mix without CMT. Even so, all specimens at 28 days still meet the minimum strength requirement for the structure walls, which are like 2068 megapascal or like 3000 psi. And in study one, we tested three different cases to evaluate how well the machine learning models could predict new data, specifically new values of coppermine tailings content, water to binder ratio, and like curing times. And in case one, the parity plot shows a strong agreement across all machine learning models, and the data points are evenly distributed around the black line, which represents the ideal condition where the predicted compressive strength equals the actual value. And this means that all the models were able to accurately predict the compressive strength of a cement paste with new amount of coppermine tailings and water to binder ratio that were not included in the training data. However, we introduced the new curing ages or combinations of new CMT amounts, water to binder ratios, and curing ages. The models were less accurate. They could not predict compressive strength as a reliably in those cases. And among all the models, the random forest model with Bayesian hyperparameter optimization performed the best overall in case number one. And to validate the parity plots, we used several performance metrics to see which machine learning model performed best. And for these metrics, lower values are better for MSE, RMSE, MAE, and MAPE, while higher values are better for R and R square and the A20 index. And based on this research, the random forest model was confirmed as the best performing model, and we then used the random forest model for the further analysis, including sharply additive explanation and partial different dependence plots, which is a PDP, to better understand how each variable affects the compressive strength. And the random forest model trained used our case one data, which predicts the compressive strength of cement paste with a new amount of coppermine tailings and water binder ratio, was used to generate a predictive compressive strength curve over curing age. And in the graph, the points represent the experimental data. Which is the actual values, and the line represents the model's predictions. And the results confirm that our machine learning model can accurately predict compressive strength for new CMT contents and water to binder ratios, but it not doesn't perform as well when predicting new curing ages. And we also expected the compressive strength to continue increasing after 28 days, but the predicted curve shows a plateau, meaning the model assumes the strength stays almost constant after 28 days. And from the SHAP result were used to identify which factor have the greatest in least influence on compressive strength. And for both study one and study two, the results show that curing age is the most influential factor. And while CMT have the least influence on strength. And in study 2, the effect of copper mine tailing is even smaller than in study 1, indicating that their influence on the overall strength of the mortar is limited compared to other mixed design parameters. And to see how copper mine tailings affect compressive strength, we used PDPs. And in study 1, adding up to 250 kilogram per meter square of copper mine tailings caused only a small decrease in compressive strength. And in study 2, adding up to 80 kilogram per cubic meter of copper mine tailings reduced compressive strength by just 0.12 megapascal. And these results shows that we can incorporate a significant amount of copper waste to produce sustainable construction materials with a minimal loss in strength. And to compensate for the slight reduction in compressive strength caused by tailings, blast furnace slag can be added. And our PDP results for the BFS available in our paper confirm this positive effect. So to build reliable machine learning models, we need more training data because compressive strength data for material containing copper mining waste is still limited. With combining our experimental data with open source data, even though the open source data did not include the tailings. And the correlation heat map shows that even a small experimental data set can significantly improve data representation. And in study 1, where we predicted the compressive strength of the cement paste, the random forest model with the Bayesian height parameter optimization performed the best. However, this model was most effective only for predicting new replacement levels of copper mine tailings and water to binder ratios, not for the new curing ages. In study number 2, which focused on mortar, CAPUST was the best machine learning model. And across both studies, curing age was the most influential factor, while copper mine tailings had the least influence on compressive strength. And this means that a larger amount of copper mine tailings can be safely incorporated to create more sustainable construction materials without significantly reducing the strength. And lastly, I will talk about the regolith materials and an emerging field that strongly emphasizes like sustainability and utilize the basic material is a space construction. As I will discuss in the next slide, building in a space is extremely challenging due to the long lead times, harsh environmental conditions, and limited availability of resources. And any successful like space construction project must be able to extract and process local materials such as regolith and find ways to remotely utilize those resources for building. And this concept is known as in-situ resource utilization or ISRU, and it plays a key role in enabling sustainable infrastructure beyond Earth. Lunar surface is covered with a like fine regolith powder created over time by like constant impact from the meteorites or exposure to radiation. And this radiation comes from both the solar wind and cosmic sources outside our like solar system. And in addition to radiation and impacts, the moon also experiences extreme temperature swings between day and night. And these large changes can put significant stress on any materials used for construction on the space or surface on the surface. And another major challenge in lunar construction is cost, especially the cost transporting materials and equipment from Earth to the moon. And this creates a balancing act, like materials must have enough strength to handle the harsh lunar environment, but also need to be an easy extract and process locally without requiring large or heavy equipment. So in our lab, we focuses on like investigating the material properties of like three classes of potential lunar construction materials. In following sessions, I will discuss three studies we conducted to characterize and optimize the mixed designs of like these following materials. First one is like fiber reinforced sulfur cements, and the second one is regolith based geopolymers and Burke centered regolith powder. And each of these materials offers unique advantages and the challenges for building sustainable structure on the moon. The first study, we examined how particle size affects the compressive strength of the regolith simulant-based one-part geopolymer. And as some background, one-part geopolymer is formed by reacting a precursor powder, rich in amorphous silica and alumina, with a highly alkaline solution. And the alkaline activator breaks the bond between silica and alumina tetrahedra, dissolving the powder into a paste. And this paste can be cast or extruded from to form a solid part. And as water evaporates, the silica and alumina organize into the amorphous gel known as NaSH, or sodium aluminosilicate hydrate, and the material reaches its finer strength once this gel is fully dehydrated and solidified. For lunar applications, the precursor powder would come from lunar regolith, while the sodium activator would either be brought from Earth or extracted directly from the regolith itself. And the results showed that the crystalline components of the material remained mostly unchanged after the reaction. However, a new amorphous silica phase is formed when the regolith powder was exposed to the alkaline activation solution. And this amorphous gel is important because it plays a key role in binding the particles together and forming the NaSH gel, which directly contributes to the strength and durability of the geopolymer. And the second study focuses on developing a regolith-based sulfur cement. And sulfur cements are like promising alternative to regolith geopolymers because they don't require water, and they only needed the heat to form and solidify, like which makes them well suited for the lunar environments. The goal of the project is to perform mechanical testing needed to build a fine element model of a fiber reinforced sulfur cement, and the future goal is to develop a mixed design that can be used for the large scale 3D printing applications on the moon. And in this study, we used basalt as a regolith simulant since it provides a caustic effective alternative to high fidelity simulants like KLS1. And here are some background on the sulfur cements. And the basic idea is element sulfur is mixed with the dry regolith and then heated about 20 Celsius degree. And when the sulfur melts, the mixture becomes a thick, viscous paste that can be compacted or extruded into the shape. And as the material cools, the sulfur solidifies and transforms from the liquid phase into the monoclinic beta phase, as shown on the right figure. And this process requires only low heat and no water, which makes it ideal for lunar construction. And another big advantages is that any failed or like damaged materials can be remelted and recycled, allowing for efficient reuse after demolition or repairs. And from the Raman mapping results, we found that the sulfur had very limited chemical interaction with the basalt powder, and there was no evidence of like sulfide formation along the particle boundaries, which means the sulfur mainly acted as a binder rather than chemically reacting with the base materials. And this result suggested the Bonding in sulfur cement is largely physical, and the overall performance depending more on mix design and compaction than on chemical reaction. And lastly, our lab has been exploring the use of regolith sintering and melting to create small scale parts. And these materials are especially interested because they use the regolith powder directly without any additional processing or binders. And in our experiment, like regolith simulant was heated to 1200 Celsius degree and 1600 Celsius degree to sinter and melt the material, and the result samples were then characterized with using Raman spectroscopy and SEM microscopy to study their microstructure and phase composition. And the long-term goal of this study is to apply laser powder bed fusion to additively manufacture complex parts directly from the lunar regolith powder, enabling on-site fabrication for the future space applications. And the melted sample shows like clearly sign of the recrystallization and a loss of the original powder morphology, like meaning the individual particles had fully fused together into a dense glassy structure. In contrast, the sintered sample retains their distinct particle shapes, with the particles bonded together at their like contact points while still maintaining a visible granular structure. And these results shows how processing temperature strongly influences the finer microstructure, with the sintering preserving particle features, and melting producing a more homogeneous and fused material. And lastly, I would like to thank all the members of research group and our collaborators for their valuable contributions. And I would also like to especially thank my PhD students, Saleh, Eka, Federico, who has been leading much of this research I presented today, and our postdoctoral researcher, Dr. Hang Jeng, for their great effort and dedication to this work. And thank you so much for listening this presentation. And if you have any questions, please let me know.
Yeah, thank you so much for this amazing presentation, Professor Hee-Jeong Kim. We're going to open now for Q&A session, so whoever have questions can send questions in the Q&A box. There's like next to, like in that like main thing, you can see Q&A box, and you can send any questions you might have and take advantage of this live opportunity. Just quickly before we go into any questions, I want to invite you guys for the next our next speaker that we're gonna have our a webinar. So in December 16, we're going to have Professor Nishan Garg, Associate Professor at the Department of Civil and Environmental Engineer at the University of Illinois Urbana-Champaign, and he'll give you a talk in accelerating and automating testing of cement-based materials from days to minutes. It's going to be a great talk. We're going to send an email this week inviting you guys, so please sign up. So I see there is a question here for you, Professor Hee-Jeong Kim.
Yeah, for the studies, we didn't do any pre-treatments. We just collected from the site, and we got the sample, and we used the sample for the studies. I was answering
Yeah.
questions for the like, have you done any like pre-treatments for the copper mine tailings? But in future studies, we plan to do the like proper treatment for the like environmental safety issues. So we're planning to do that.
Yeah. Also, I have a question, Professor Hee-Jeong Kim. So regarding like the use of tailings and cementitious materials as that often we have issues regarding the rheological behavior when we use like supplementary cementitious material. Do you have any insight of how the tailings are impacting that? Because even though I know like we normally keep the water cement ratio constant here, but do you have any insight on that, of how if it like increases a lot the water demand or how it's impacting?
So we are trying to like minimize the like any kind of effect. So we use the less amount of the CMT for compensating those problems. But usually we used it as a like aggregate doesn't matter at all, but I can say that like as you mentioned before, like if we use that as a supplementary cementitious materials, it will be very tricky. So we have to come up with the proper material design and studies to do that.
Yeah, thank you. And we have another question on the Q&A box. So did you find any issues like leaching for the CMT?
We also checked the like leaching behavior, and we were able to confirm that like the cement matrix can fix the heavy metals from the CMT or GMT. But to strengthen our fixing mechanisms, we also plan to use like geopolymer so that like heavy metal can be encapsulated in like aluminosilica chain in near future.
Okay. So I don't know. Yeah, you guys have like a few seconds. Okay, we have another question. For thermal activation, okay, so I'm gonna read the questions. For thermal activation of mine tailings basalt mines, we need to go up high temperature to amorphize the crystal and get reactivity. Can we add any fluxes to lower down the temperature of thermal activation?
We may be able to use like chemicals to lowering down the temperature of the thermal activation, but like we plan to do these studies in near future.
Okay, so we have another question here. In your opinion, what is the most accurate technique to characterize CSH?
So in my opinion, since the CSH, like we don't know about very much about it, and it's how can I say amorphous material. So like in these studies, we were able to like check their structures with using confocal Raman spectroscopy, and I do believe with using Raman techniques, we can also like characterize CSH properly. But if you also want to check other properties, we can also come up with a different kind of characterization technique.
Also, going again in this characterization technique, that was an interesting question. I've been seeing like more and more ramen as a characterization like method. So I'm not super actually familiar with like that method. So it was interesting to see you're using it. So are we able to have like really quantitative like data regarding both like characterization and hydration formation with ramen?
So we actually did compare with like other technique characterization techniques such as like setting time, hydration of heat to show like their hydration of degrees with supporting data of like how much hydrate are formed within visualized Raman metadata. That's one way we can also confirm the hydration kinetics with the other techniques in Raman spectroscopy.
Mhm. Okay, okay, thank you so much for today. Thank you everyone for attending this webinar. Okay, so I think we don't have any more questions, but yeah, I really appreciate your taking your time today and being with us and showing your amazing work. So thank you so much, Professor Hee-Jeong Kim.
Thank you so much.